All right, so let me start. Ladies and gentlemen, dear colleagues, welcome to the scheduling seminar. Today we will have a talk by Federico Della Croce. Federico is full professor at the Department of Management and Production Engineering at Politecnico di Torino. He teaches master courses like decision making and optimization and quantitative methods and decision aid. And he also teaches operations research in bachelor courses. Federico published amazing number of scheduling papers in computers and operations research and Azure. And up to my feeling, he is developing and developed many scheduling algorithms, for example, for Job Shop, Flow Shop, or Italian Football League. Look into his profile to see more. And beside of that, he is very charming person with good-looking smile, at least at the picture that he has put on our web. So Federico, the floor is yours. Go ahead, please.
Thank you very much, Zdenek, and thanks to you, to Michael, and to Guohua for inviting me for this scheduling seminar. The reason for which I decided to talk about the longest processing time rule is that the work I did with Rosario Scatamacchia, who is also professor here at Politecnico of Torino, is that, first of all, I had a lot of fun with this work, and doing research is always fun, but this time it was even more. And the second reason is because in this case, we had the opportunity of merging, putting together, melting, in a sense, approximation and heuristics, which is, at least I was not that much used to, and it did work in that case. And the final thing is that I like very much using linear programming modeling, and in this case, we managed to use linear programming for approximation in, let's say, a not fully standard way, let's say. So that was also very, very, a nice thing for us. So let me go with the, let me see. Okay, that's fine. This is the outline of the presentation. I will start with a gentle, let's say, introduction. Then we're gonna talk about identical parallel machine scheduling. So we'll see the longest processing time rule, and we'll see some properties of the longest processing time rules. And in a sense, let me say that we will see constraints and requirements induced by the longest processing time rule, keeping in mind that at some point we play with linear programming models for that. From that, we find that in terms of approximation, so worst case performance of the longest processing time rule, there is clearly this a set of tight bounds for different values of m, and so we have to work on those. And for that, we look for an improvement to LPT, and that improvement is actually a slight modification of LPT, and this to reach, let's say, this improved approximation result. And from that, we had an idea for doing, for devising a heuristic, and that is the fourth part of this presentation related to what we call the slack rule, and then some conclusion. So, well, generally speaking, what can I say? We know that every standard undergrad course on OR embeds a section devoted to ELP modeling. So if we think about linear programming modeling, well, we use those, generally speaking, to provide formal representation of real problems. Nowadays, of course, we try to solve those problems. So if you have good knowledge of those problems, then we can try to solve those problems by just applying the corresponding ELP solvers. But unfortunately, it doesn't work that well. And by the way, it typically doesn't work that well on scheduling, and generally speaking, on sequencing problem. Or else we may conceive finding out heuristic solution, for instance, by applying math heuristics. So where we have some general local search approaches that embeds the solution of ELP subproblems, which are solve to optimality pretty fast. I'm talking about the subproblems and induce somehow a heuristic out of it, or possibly derive the approximation bound. So we focus here to the fact of deriving an approximation bound on some given problem. And if we do that, typically, I mean, what we are used to see is to have a related ELP formulation that presents some structural properties, so that, for instance, solving the continuous relaxation, we derive something, and from that we get a solution and corresponding an approximation bound. So to move on, let's say that we will denote by opt the optimal solution value, and let's say that we denote by A the solution value of some given approximation algorithm. Then we are interested in the so-called performance ratio, R of A, which is A divided by opt. And of course, we're interested in the worst cases that corresponds to the approximation ratio. And even though nowadays there is quite a bit of research on exponential, let's say moderately exponential approximation algorithms, here we're just focusing on the standard research for approximation algorithm require polynomial time complexity. So as an example, imagine we consider the minimum vertex cover. And so we have a graph G with a set capital B of vertices and a set capital of E of edges. And we say that the vertex cover of G is a subset of the vertices in V that covers, that is, that touches every edge in E. So if you see this figure, we have two graphs, one on the left part and the other on the right part. And the red vertices, both on the left part and on the right part, represent covers. But in both cases, let's say the graph below is, so the one I'm indicating here is actually the one that provides the minimum cover with respect to that one, or else if I take the picture on the right, this graph here is the one that provides the minimal vertex cover. Minimum vertex cover is one minimum vertex cover. This problem is one of the well-known problem in combinatorial optimization. It is equivalent to maximum on click, maximum independent set, and so on and so forth. But if we consider this problem here, we can come up with a standard ELP formulation, which is quite simple. Imagine that we assume that we put binary variables xi, where xi is equal to 1 if vertex I is in the cover, while vice versa, if it is not in the cover, xi is equal to 0. And then in this case, if you want to find the minimum vertex cover, we want to minimize the sum for all I, the sum of xi, and with the constraints that for every edge E, the extremities of E, one of the two extremities, so one of the two vertices, either I or J, if I'm talking about a given edge ij, xi plus xj must be greater or equal than 1, where we have binary variables. So imagine that we consider the relaxation of this problem, in which we just, instead of having binary variables, we have continuous variables. Then we have the corresponding problem here. This problem is polynomially solvable, but actually, if we take the continuous solution and then we set xi equal to 1 for all variables which are greater or equal than 0.5, on one side we have a feasible solution, and on the other side, this solution is no more than twice the continuous relaxation solution. So we have, in this case, a two approximation ratio, which is reached actually by what I mentioned here as standard ELP modeling. This is not what we want to do, but just to say that typically approximation used linear programming models in this way. Okay, the idea here for the work I'm talking about is to apply what I mentioned as non-standard ELP modeling as follows. Imagine that we try to mimic by ELP model, by using an ELP model or several ELP models, the behavior of a procedure. So in this sense, we typically refer to greedy procedures, because it becomes somehow doable the fact of representing the behavior of the procedure by constraints, and then an objective function to find the worst case. So we apply this approach to machine scheduling, and so we consider problem Cmax, where we want to minimize the makespan on identical parallel machines, and the so-called longest processing time rule. So let us see how it works. I guess that probably all of you know it, but for those who may be a little bit less familiar, imagine that we have m identical parallel machine mi, I going from 1 to m, and we want to schedule n jobs on those machines. And the problem indicated with the three-field notation as Pcmax, or let's say PM Cmax, if you want to point out that there are exactly m machines, requires to minimize the maximum completion time. And we consider the famous longest processing time rule, which is indicated actually below, and that was proposed roughly 50 years ago by Richard Graham. And the longest processing time rule says, just sort the jobs in descending, let's say, non-ascending order of their processing time Pj, and then assign one job at a time to the machine whose load is smallest so far. So if you look at the picture there, the largest jobs are the blue jobs, and if we assume, as it is in this picture, that we have 3 machines which are indicated like here. So this is the first machine, this is the second, and this is the third. And imagine this is the corresponding Gantt diagram. So the largest job is the blue job on top. Then the second largest job is the second blue job in the middle. The third largest job is the third is the blue job on the below. And similarly, the other 3 jobs, which are the gray jobs, are the 4th, the 5th, and the 6th largest job. And then the smallest job is the black job here. So if we apply LPT, or we take the largest job and we put on some given machine, imagine that we put it on machine 1, and corresponding we put the second blue job on machine 2 and the third blue job on machine 3. And then as the smallest load is on the third machine, we'll put the largest gray job on the third machine. Correspondingly, we're going to put the second largest gray job on the second machine, and the smallest gray job on the first machine. And then if you are here, you see that the completion on machine 3 is here, the completion on machine 2 is in between, the completion machine 1 is larger than the completion machine 2 and smaller than the completion machine 3. And so the machine whose load is smallest so far is the second one, and we put there job J, the black job. So this is the simple LPT rule. Let us see the properties of this rule, and for doing that, let's have some notation. So assume that the jobs, first of all, are indexed by decreasing Pj, or more precisely by non-increasing Pj. So Pj is greater or equal than Pj plus 1 for all j. And then let us denote by CLPT and by C star the makespan obtained by the LPT rule and by the optimal solution, where we put as a subscript m when we refer to the fact that we have a problem with exactly m jobs. Also, let us denote by RK the performance ratio CLPT divided by C star when there are exactly k jobs assigned to the machine that provides a makespan. The machine that provides the makespan is typically indicated as the critical machine. Finally, let's say that we denote by J prime the critical job. That is the job that induces the makespan, so is the last job on the critical machine. There are a bunch of properties, let's say a bunch of constraints of conditions that we can write down. First of all, we know that the optimal solution is at least the values of the largest processing time. This is straightforward. As much as the best we can do is to exactly balance the jobs on all the machines. So even if we do that, then the completion time is at least, so the optimal solution value is at least the sum of the processing time divided by n. Also, what we can say is, I mean, as a result of LPT is that the makespan obtained by LPT is actually optimal if the value of the processing time of the critical job is strictly greater than the optimal solution divided by 3. So this is some information we keep in mind, because saying this implies that if you want to analyze CMLPT, we want to check, we want to deal with the fact that LPT may be not optimal. So in that case, we're going to say, well, then it's the processing time on the critical machine must be smaller or equal than C star divided by 3. And then there is the result obtained by Graham, and you can have a look, as mentioned by, was mentioned to me actually by Jan-Karel Lengstra, that if you go to elements of scheduling.nl, which is a nice portion of the book that never came up, but at the very end, but some of the chapters still are available and they're interesting. Well, you can see simple proof, I mean, a nice proof of the result by Graham, but generally speaking, what we can say is that we know that the performance ratio of LPT in the worst case is not superior to 4/3 minus 1 divided by 3n, okay? And finally, there are some other results. For instance, we know that if we have a given job I assigned by the LPT rule to a given position J on a machine, that we know that PI must be smaller or equal than the optimal solution divided by J. What I'm just saying is all these are constraints, and actually all these are linear constraints if we consider M as a constant. Among the performance ratio, we know that R1 is equal to 1. Of course, if LPT makes one obtained by a single job that is the largest job, the solution is optimal. We know that R2, so when the critical job is actually the second on a given machine, is a little bit better than 4/3 minus 1/3m, because it's 4/3 minus 1/3 times m minus 1. This is a result by Chen. And this is the result, I mean, the relevant result by Graham, the R3, and this is the result we would like to improve, let's say. And more generally, Kaufman and Sethi show that Rk is not superior to k plus 1 divided by k minus 1 divided by kn. So, said it differently, what he can see is that, well, R2 is equal to 1 when we have just 2 machines, that R2 is equal to R4 when we have 3 machines, and R2 is smaller than R4 when M is greater or equal than 4. And then Rk is smaller than Rk plus 1 for every k greater or equal than 3. Said it differently, the issue is that if we are able to improve our R3, then we are able to improve the approximation ratio by LPT. So we focus then on instances where the critical job is indeed in position 3. So we somehow restrict our analysis to try to improve things. The tight worst case examples for LPT are all, there is a family of examples of this type. So you see if you have 2 machines and 5 jobs with 2 jobs with processing time 3, 2 jobs and 3 jobs with processing time 2. We're gonna assign to the 2 machines the first 2 jobs with processing time 3. Then we're gonna assign to the 2 machines the other 2 jobs with processing time 2. So both machine completed times 7. And then we add the last job on one of the 2 machines, and correspondingly, the makespan obtained by LPT is equal to 7, while the optimal solution is equal to 6, in which you put the first 2 jobs on one machine and the last 3 jobs on the other machine. And so the ratio is indeed 7/6, that for 2 machines corresponds to 4/3 minus 1 divided by 3m. Well, actually, this example is always can be generalized to m machines. For 3 machines, These are the data we need. And generally speaking, for n machines, it is sufficient to consider 2 jobs with processing times 2n-1, 2 jobs with processing time 2n-2, till up to n+1, and then eventually 3 jobs with processing time n. And if we do that, LPT finds a solution which is for n-1, while the optimal solution is 3 over n. So what we can see is that actually the workspace is very peculiar because we have exactly 2n+1 jobs. And so the number of jobs is indeed 2n+1. The critical job is the last job, so the smallest job, it is in position 3. And the optimal solution is the best we can hope for, because the optimal solution actually hits the bound sum of the processing time divided by n. So it's very peculiar. Okay, if we just consider talking about LPT, then we'll see what we're going to do when we consider also something different. Then we can assume that the critical job is the last one. So J prime is equal to n. Because if not, the analysis would be the same, but just removing the other jobs, so that the solution by LPT remains the same, while the optimal solution can only improve. And so we have to consider, we focus here on at least 3 machines. At the very end, I will discuss a little bit the case with just 2 machines. We focus on the fact that n is in between 2n+2 and 3m. Why so? Because suppose that n is critical and n is larger than 3m, then the critical job would be the 4th one. And so we already would be able to reach a better performance ratio and, globally speaking, a better approximation ratio. So either m is between 2n+2 and 3m, or n is equal to 2m+1. And whenever n is smaller than 2m, it is possible to show that LPT actually reaches an approximation ratio, which is already a little bit better because it's 4/3 minus 1 divided by 3 times m-1. And we employ linear programming to perform the analysis. Let us see how. So the idea is, so imagine that we are considering the fact that we have 2n+2 jobs. So this implies that there is at least 1 machine that has at least 3 jobs. And so if LPT schedules at least 3 jobs on a non-critical machine, then we can show that LPT has an approximation bound which is already bounded above by 4/3 minus 1 divided by 3 times m-1, which is better than 4/3 minus 1 divided by 3n, which is the result we want to find. We focus here for the case where m is greater or equal than 5, then we'll move on for the cases m equal to 3 and 4. So let us see the proof, and the proof is just the linear programming model. So we assume that job n is in position 3, or else we would have either R2 or R4. So there is another job. Sorry, let me do this. There is another job that schedules, another machine that has at least 3 other jobs. So you see, LPT schedules at least another job in position greater or equal than 3. So we consider an LP model where we can arbitrarily set to some given value the makespan. So we say that the makespan is equal to 1, for instance. And our goal is to minimize the optimal solution value. And so we have a bunch of variables. So let us say that capital L denotes actually the starting time of the critical job. So what we know is that CLPT is equal to capital L plus the processing time of the critical job, that is the last job, that is Pn. Also, let's say that C1 denotes the completion time of another machine, another non-critical machine that processes at least 3 jobs, because we have at least 2n+2 jobs, so there is at least another machine that processes at least 3 jobs. And then let us denote, but this, I mean, just the definition, let's say that C2 is actually the sum of the completion time of all the other m-2 machines. So actually C2 is equal to the sum of the processing time minus C1 minus CMLPT, so minus L plus Pn. Then, due to this scheduling, we can say that capital L, which is the starting time of the critical job, must be inferior to C2 divided by m minus 2. C2 is the sum of all completion time of this minus of the m minus 2 machines divided by m minus 2. What we get is necessarily must be greater or equal than capital L. And also, as n is in position 3, we know that Pn must be smaller or equal than Cm star divided by 3, because there are at least 3 jobs in the optimal solution, because there are at least 2m plus 2 jobs actually. So we just generate processing corresponding non-negative variables, Pn and sum P correspond to Pn and the sum for j going from 1 to n of Pj. We associate the corresponding non-negative variables C1, C2L, and OPT to what we mentioned before. So OPT stands correspond to the optimal solution. And so the LP model is I will explain it in a little bit more, but what we do is that we minimize the optimal solution value. We guarantee that the LPT value is equal to 1. We could put any value, 1, 100, 1000, whatever. And then there are a bunch of constraints that we need to respect. Let me show you, let me mention that here we have, if m is given, we have just 6 continuous variables. To be more precise, well, we minimize the solution, the optimal solution value, where we guarantee that the LPT solution value is equal to 1. We want then m minus n times OPT plus sum P is more equal than 0. That says that the optimum solution value is at least the sum of the processing time divided by m. We need a constraint 3Pn minus C1 is more or equal than 0, because we know that we have in the optimal solution at least 3 jobs with processing time greater or equal than Pn that are assigned to a non-critical machine. We state that L minus C1 is more equal than 0, that is the completion time of the critical machine before the last job is loaded less than the completion time of the other machine processing at least 3 jobs due to list scheduling. Also, constraint finally is due to list scheduling. And finally, constraint 6 just tells us that sum P indeed represents the sum of the processing times. Finally, we have the final indication that says that the optimal solution must be at least greater or equal than 3 times the smallest processing time, and the fact that all variables are non-negative. What is interesting here is that for any fixed m, we have a linear programming solution. So that was nice, but the better thing was that by applying strong duality and a little bit of reverse engineering, so by using a standard technique of operations research, then what we can see is that the value of those variables can be derived for any m. And so, roughly speaking, what we obtain is that opt is actually equal to 3 times n minus 1 divided by 4n minus 5, and correspondingly, and this is the worst case possible because we are minimizing the value of OPT. And so the ratio, so the performance ratio by LPT and the optimal solution is not superior to 1 divided by OPT, which is actually the reverse, I mean, the inverse of the value here. So we get 4m minus 5 divided by 3 times n minus 1, which corresponds to 4 over 3 minus 1 divided by 3 times n minus 1. This is just algebra. But the nice thing is that we managed to say that indeed, whenever we have at least 2m plus 2 jobs, LPT already does the job. So we get an improvement with respect to the performance ratio, I mean, to the worst case performance ratio indicated by Guerrero. Notice this bound is not tight. So potentially we can further improve this value, but we know that at least this value is correct. Now, I will go fast on these other things with similar analysis, and sometimes actually we needed some partial enumeration. We managed to prove these things also for m between 3 and 4. Also when n is more or equal than 2m and m is greater or equal than 3. and also when m is greater or equal to n3, and where n is equal to m plus 1, but where LPT loads at least 3 jobs on another machine, on a machine before the critical job, okay? So what we managed to say is that we remain with just one single case, our type bound, and this is the single case is where n is equal to 2m plus 1, and where LPT schedules jobs, job n only interposition, and n it must be critical. So we can work on that, and we consider a slight algorithmic variation of LPT. So what we do is the following. Let's assume that we have a variable of LPT that we call LPT of S, where S represents the set of jobs assigned altogether to a machine first. And in particular, consider this algorithm in which we have 3 machines, we have n jobs, and what we do is simply apply LPT and get 1 makespan, and then apply LPT prime, where we first take the critical job and we put it on a single machine, and then we apply LPT. And we want to return the minimum between these 2 values. So in practice, what I mentioned here is that the algorithm applies first LPT and then reapplies LPT, just having loaded to one machine at the beginning the critical job J prime. If we apply both LPT and LPT prime, we have a bunch of subcases. The analysis, again, is similar to what we did before by using some linear programming, but let me make some further, just a further example. So let me consider just one specific example among the subcases we have to consider. So the possibility is that either n is equal to j prime and we have exactly 2m plus 1 jobs. And in that case, the processing time of the smallest job either is greater or equal than P1 minus PM, or is strictly smaller than P1 minus PM. Or else we have more than 2m plus 1 jobs, because indeed J prime is critical, but for LPT, but then the critical job in LPT prime is another. And this job I may be larger than J prime or smaller than J prime. Okay, so we're going to focus on this, let's say, blue case, where n is equal to 2m plus 1 and P2m plus 1 is greater or equal than P1 minus Pn. So the issue is the following. By, let's say, splitting all possibilities, so by doing some sort of a reasonable enumeration, we are focused on a given problem with specific various specifications. So particularly we have exactly 2m plus 1 jobs. Particularly we have that the processing time, the smallest processing time, it must be greater or equal than P1 minus Pn. These are constraints that we can use. But also, if we are in this situation, what we can show is that necessarily LPT has a very specific schedule. So LPT will have job 1 on machine 1, job 2 on machine 2, job 3 on machine 3, up to job M on machine N. And then, so we go down in this way with the first M jobs, and then we go up in that way with the second M job. So M plus 1 is on machine M, and M plus 2 is on machine M minus 1, up to the job 2M is on machine 1. And eventually the last job will be assigned to some machine with minimum completion time. So we know that the property, the characteristic of the problem is this one. And corresponding, those are the relevant completion times of the various machines. I don't want to stick to this. I mean, I'll move on, because the problem is not providing you all this data, but the fact of saying, okay, there is structure and we can use this structure. So if we now analyze LPT prime, what we can say is that indeed the structure of LPT prime is such that again, we're going to have job 2m plus 1 on machine 1, then job 1 on machine 2, job 2 on machine 3, up to job m minus 1 on machine m. And then we, at this point, we're going to add job m here, because this is the smallest, the machine with the smallest load so far. And then we go back there. So we would put job m plus 1 on machine m, job m plus 2 on machine m minus 1, and so on and so forth. And eventually, we necessarily going to put job 2m on machine 1. So this is the structure of the problem, and we have this information here. And so then there are some options. Either LPT prime has the makespan on machine 1, or LPT prime has the makespan on some other machine. So by considering these subcases, I will consider just the first one. Actually, the second case is a general case, so I'm not going to consider M some case. I need just one case. What we can say is that we managed to find out this improved result because as a result, we managed to obtain a further inequality, that is that the optimal solution necessarily must be greater or equal than Pn minus 1 plus Pm. You see structure induced by this, let's say, partial enumeration. And eventually, if this value holds, these values hold, so if P2m plus 1 is greater or equal than P1 minus Pm, and the makespan of LPT prime is equal to this value here, so let's say that the critical job is on the first, the three jobs on the critical machines are these ones. Then we have an approximation ratio which is constant, is actually not superior to 7/6. And again, we can do that by using linear programming. What we just need to do is to put variables xj corresponding to the processing times. Recall the fact we are talking about M machines. So potentially we have an infinite number of variables if M is very, very large. But the interesting part is that we don't need to write all the constraints, but just some of them. So if you see here, what we are just saying is we have a bunch of constraints in which we just say that the optimal solution value must be greater or equal than xm minus 1 plus xm, that the optimal solution value is necessarily at least the sum of the three smallest jobs, so x2m minus 1, x2m, and x2m plus 1. We want to maximize, so the worst case of our LPT prime rule, x2m plus 1 plus xm plus x2m. And the other constraints here are just a constraint that says that the largest job is job 1, the second largest job is job 2, etc., etc. But as you see, I'm using here just some of these variables. So we don't need to consider all variables, but we just need to consider variable, the processing time of the first job, the processing time of the n-1's job, of the m's job, of the m plus 1 job, and 2m minus 1, 2m, and 2m plus 1. See, so we just need 7 variables for that, 7 xi variables plus variable OPT. And all these are the constraints I was mentioning there. If we do that, by setting OPT is equal to 1, the cost value, the cost function is equal to 7/6. So we can use the property, the strength of a linear programming continuous model to reach an approximation ratio, a worst case performance ratio. So if we put everything together, what we can say is that if we apply actually LPT plus LPT prime, we can manage to have an approximation ratio which is not superior to 4/3 minus 1 divided by 3 times n minus 1. I showed you just a couple of examples. The real proof need to consider several examples, but I mean a number, say 7, 8 examples, different 7, 8 subcases, right? Okay, let me move on. From the approximation, what we notice is that for n greater or equal than 3, the relevant subcase was actually provided by this processing time, P2m plus 1, which was actually larger than P1 minus Pm. So in a sense, the issue was that we had the M, how can I say, M machines. And when we consider M machines, actually we have we have just 2m plus 1 jobs. So you may say, okay, I may have a portion, subsets of jobs, say the first M jobs, the second M jobs. Here we have just one job after. But we can try to conceive this thing here. And so what we thought was why can we can think of list scheduling, but apply to let's say, tuples of jobs. So the proposed approach that we mentioned as split, as Slack, splits the job set in tuples of m consecutive jobs. 1m, m plus 1, 2m, 2m plus 1, 3m, etc., etc. And sorts the tuples in non-increasing order of the difference between the largest job and the smallest job in the tuple. So P1 minus PM, PM plus 1 minus P2M, and so on and so forth. Then we apply list scheduling, but to the sorted set of tuples. We call this approach Slack, and it works as follows. We sort the items by non-increasing the jobs by non-increasing Pj. Then we consider tuples 1m, m plus 1 to m, n minus m plus 1, n, where we add dummy jobs with 0 processing times if the ratio n divided by m is not integral. So if we have 7 jobs and 3 machines, we're going to add 2 jobs so as to have 9 jobs, which is a multiple of 3. And then for each tuple, we compute the associated slack, P1 minus PM, and so on and so forth. And then we sort the tuples by non-increasing slack, and we apply list scheduling to this job order. So by doing this, this is the example, the worst case example for LPT with 3 machines and 7 jobs. This implies that we're going to have, instead of 5, 5, 4, 4, 3, 3, 3, we're going to add 2 jobs. So we have 5, 5, 4, 4, 3, 3, 3, 0, 0. So the tuples are the 3s, 5, 5, 4, 4, 3, 3, 3, 0, 0. And if we sort them by slack, 3 minus 0 is 3. And those values are equal, so 5 minus 4 is 1, 4 minus 3 is 1. And so the sorting will be 3, 0, 0, 5, 5, 4, 4, 3, 3. And by doing this, for the example there, we actually get that the Cmax of Slack is 10 and not 9. And by the way, the running time of Slack has the same complexity of the running time of LPT, because we stick the only important part, what can I say? The hard part that takes most of the time is just sorting the set of jobs. So we compare Slack to LPT on the benchmark instances. Let me see what time it is. Yes, I have time. So we have 2 classes of instances from the literature, the so-called uniform instances and the non-uniform instances. In the uniform instances, the processing time are distributed in the range A, B, where A is equal to 1 and B is either 100 or 1,000 or 10,000. In the non-uniform instances, the distribution is the one you see here. So, they have some peculiarity, let's say. And for those classes, were considered 5, 10, and 25 machines, and the number of jobs from 10 up to 1,000. So globally speaking, having 10 instances for each pair MN, we have a good number of roughly 800 instances. And indeed, what we can see is that Slack dominates LPT. So here we are comparing the number of wins, the number of draws, the number of wins of Slack, the number of draws of, and the number of wins of LPT. And so overall, you see that on non-uniform instances, Slack wins roughly 300 times, the draw is just 83, and the number of LPT wins is about 2%. While for uniform instances, things are quite similar. Maybe LPT works a little bit better, but roughly speaking, we see that there is quite a bit of a difference. And what else? Having compared Slack to LPT, there are some more competitive heuristics available. I'm talking about constructive rule and things like that. I'm not talking about, meta heuristics or whatsoever. And so what we can notice is that it actually is also superior to Combine and slightly inferior to the differencing method by Carmarker and CART, even though it's much, much, much faster. And so if we just add a simple neighborhood search in Cascade, then Slack plus this small step of neighborhood search already gets better results than LDM, being, however, more than an order of magnitude faster. So what else? As a conclusion, what I can say is that we show that non-standard ELP modeling can be applied to derive the approximation results. We did this here on the parallel machine problem with makespan as objective function by revisiting the LPT rule. I recall you, we were mentioning the fact that typically we consider the fact of using constructive procedures. This is because this allows the fact of adding constraints in the relevant linear programming formulation. Biosimilar analysis, together with Rosario Scattamacchia and Vincent Kint, we were able to get the linear time algorithm for the problem with two machines. The algorithm is a little bit different, but again, it runs in linear time and gets this ratio. Of course, I mean, P2 Cmax is in a sense is subset sum, so there exists an F-betas on that. And I mean, for n given also for P Cmax, there are approximation ratio. The goal here was to find specific approximation ratios with constant approximation ratio requiring very small processing time, so typically O(n) square or n log n at most. And we think that this, let's say, LP-based analysis, we did some work on that, for instance, on some knapsack problems. This analysis can be applied also in other problems in approximation theory. And we see this as a valid alternative for formal proof systems based on closed form and analytical derivation. And this concludes my presentation. The blue reference here is actually the paper that describes in details this approach. Thank you very much.
Okay, Federico, thank you very much for your talk. So I think that everybody should be able to ask a question now. I'm right. So everybody should be able to unmute himself or herself. And let me ask the first question. When we look on LPT rule, we have impression that if there is enough of short tasks, if there are many short tasks, then it's easy to achieve optimal solution, right? So in your analysis, did you consider also some distribution of processing time among the tasks, like certain portion of tasks having a short processing time?
Well, in the distribution, let me go back here. We used, I mean, this distribution. Let me go back. That we have there. So we go beyond, let's say, these benchmark literary instances with respect to that. Okay, but have you considered it for some well, you see that those, I mean, the so-called non-uniform instances do have some specific value which are kind of peculiar. I'm just saying that. And I mean, we did not say, okay, let me try to see what happens when there are specifically so many small processing times. So that I agree. I mean, we know that in convergence LPT is optimal, by the way. Yeah. So, but you don't know any work which builds approximation factor based on specific distribution of No, I can't tell anything with respect to that now. Yeah. Okay, so is there any questions? So just unmute yourself and ask if you have a question. Nobody is asking, so you're wondering if I really... Jan Karel is asking, but... Okay, Jan Karel, please go ahead. He's having troubles in unmuting himself, I guess. Mm-hmm. So... it should work, right? But I don't see. If there is no.
question.
Maybe the question was so nasty that they don't allow him to
It's not allowing to unmute. So I am not allowing to. So on my screen it shows like that everybody should be able to unmute. But so I will switch it once on and once off. So you can also ask your question in chat, and we can read it from the chat if it doesn't work.
I think we can unmute now.
Okay.
Yes, there we are.
Okay, it works. Sorry
Okay.
for that. Okay.
Federico, thank you for your nice talk. You said that when you add a simple neighborhood search to your heuristic, then you beat car. Is it due to your method as a starting solution, or is it simply due to neighborhood search? Because I would guess that if you start from any starting solution, simple neighborhood search is likely to beat any of those advanced constructive heuristics.
We started by let's say the solution obtained by Slack. So the solution is already quite good. So the number of neighbors that you need to perform is very limited. The issue was just to check whether in terms of CPU time, you were able to reach the same results or similar, and if the CPU time requested was not important. And by the way, I mean, the neighborhood was very simple. I mean, just swapping jobs. So we're not even considering couple or triples of jobs, just to make it running very fast. So what we noticed is that we were able to improve the solution. We having still a CPU time that was roughly 1 order of magnitude less than the one of the differencing method.
Okay, so
but yes, I agree. I mean, I'm not questioning the fact that by doing local search you can improve it. But if you start from a random solution, then you may need quite a bit of moves.
Yeah. So you're talking now more about running time than about quality. I understand. One other thing, it is interesting that you use linear programming to prove worst case guarantees. We recently published a paper in our letters where we used pretty complex LP analysis for proving performance guarantees for a graph theoretical problem. I'll send you the reference.
Yep. Thank you very much.
Okay.
There is something. I mean, I've seen something. I mean, I did it here, but at some point I recall I forgot it, but I refereed the paper, say 2 years ago, and again there was something similar on a different problem. Okay. So I think there is something which are moving up and down with respect to that.
Okay, thank you.
Thanks to you.
Okay, anybody else?
Basically, with regard to scheduling on parallel machines, of course, you have multifit, which has a performance of 13/11. If you are saying that you are trying to find a solution to scheduling on parallel machines, then you would have to compare to those types of results as well, and also to average performance of multifit. I appreciate the other results, of course, but I'm saying it's not solving the problem in a better way. Or you didn't show that it is solving the problem in a better way.
Sorry, I missed the question because I missed some of the words. I didn't hear you.
Did you? Basically, my question is: did you? I'm not sure. Are you? I do not think you were claiming that you are solving the problem in a better way. You said that you made a new method in order to improve performances of heuristics using linear programming.
I'm saying that we get an improved approximation ratio by using this, slight modification of LPT. So basically, what I'm saying is that by using LPT and LPT prime, the approximation ratio goes from 4/3 minus 1 divided by 3m to 4/3 minus 1 divided by 3 times n minus 1. Of course, I showed just a couple of examples and on because I have something like, as I mentioned, 8-9 subcases to be considered that I could not present in here. But the overall results says that. Was this the question?
Yes, it answers half the question because you are not trying to say that you improve the solution of the problem itself. You improved LPT, you did not find a better solution for this problem.
What do you mean with a better solution for this problem?
Okay, I'm just saying there is multifit which provides an approximation ratio of 13 divided by 11. Therefore, maybe you could look at that, whether your method works, but it's much more complex than LPT, so it probably won't.
Yeah. I mean, here the issue is with respect to this kind of complexity also in terms of CPU time. Yeah, okay, I understand what you mean when you say the quality. Yeah, sure. Yeah, okay, that's
fine. It's our again. Right. Thank you very much.
Okay. Any other question? If not, so thank you very much, Federico. It was a nice talk. And let me remind you that the next talk will be given by Benjamin Mosley, and it will be about machine learning for scheduling problems, right? It will be in 2 weeks. So thank you very much for being with us, and hope to see you in 2 weeks.
Yeah.
Bye-bye.
Bye-bye. Thanks to all.